So hello everyone, my name is Prateek Tripathi and I'm a PhD student at Imperial College London. I'm supervised by Professor Pantelis Georgiou and Dr. Nicolas Moser. And today I'm here to present to you a novel approach about in-pixel detection of nucleic acid amplification using neuromorphic ISFET arrays. I'll begin with a bit of background, provide you the motivation for this approach, then I'll present the novel biosensing principle, followed by the pixel architecture, results, and conclusion. Ion-sensitive field effect transistors, also known as ISFETs, are basically MOSFETs with a floating gate. They can be fabricated in CMOS. As you can see in the picture here, you have a MOSFET that's extended to the top metal layer. You have the passivation surface, which then has a solution that you bias through the reference electrode. You can model it, as we model everything as electrical engineers, and then you can run it in simulations through your softwares like Cadence. Any change in the ion concentration at the surface of the chip causes a variation in the threshold voltage of the device. So in essence, this is a pH sensor. Like all things in the world, ISFET suffer from non-ideal effects like trap charge and drift. Trap charge is a charge that gets trapped on the floating gate of the ISFET, most likely due to the charge transfer during chip production, introducing an offset in its threshold voltage. So here on the right, you have a picture of the same array. While all the pixels are part of the same array and are seeing the same pH level, you can see the offset that's present due to trap charge. Then comes in drift. Drift is a slow monotonic change in the threshold voltage of the ISFET and originates from a transport phenomenon at the interface between the insulator and the solution. So for the same pH, you can see that there's a degradation over time. That's your drift. Our group works on an application of nucleic acid amplification detection, where we use lamp assays on the surface of our sensors. We then heat this to 63 degrees Celsius, and if it's infected, you will see the release of ions, which will tell us whether an amplification has occurred or not. What we do is we use a two wells approach. So as you can see, there's a chip here. It has two wells. The top well is the sample. The bottom well is the control. And if it's a positive reaction, you will see an inflection point in the signal, which is not the case for a negative signal. But it's not that easy to see. This is only to make it easier for you guys to see. In essence, it's much well hidden due to non-ideal effects like drift. And so all past approaches have tried to figure out how to look for this inflection point using circuit techniques or post-processing. My aim is sort of to bring this onto the chip. And so that's where I take motivation or inspiration from the smartest tool in our body, the brain. And I rely on neurons, because neurons are the main learning components of our brain, and they work in the spike domain. They have a high dynamic range. They work at very low power, show cooperation, and in the end can learn new things thanks to plasticity. And this has given rise to a whole field of neuromorphic intelligence, where ever since exascale, while people are looking for new materials and devices or more efficient architectures and packaging, we engineers are looking for new models of computation and are being led by the field of neuromorphics. This is because it's analogous to the morphology of the nervous systems due to spiking. It combines analog, asynchronous digital, and logic circuits. It yields application-specific devices that are optimal for edge computing. And finally, something super interesting is that MOSFETs in weak inversion use diffusion for charge transfer, which is similar to the ionic currents in neurons. And so that presented us with a great opportunity, because we thought, hey, wait a second, ISFETs also respond to variation in ion concentrations. And so we decided to combine the field of neuromorphic circuits with potentiometric ISFET sensing. As you can see on the right here, there's the famous Hodgkin-Huxley model of a neuron. We said, let's replace these ion channels with ion channels due to ISFETs, which means we can create asynchronous event-based circuits that have a low latency and work at ultra low power. And this is already being done by companies for imaging, for cameras, like Prophecy, where you can see a lot more information is captured by an event-based sensor as compared to a frame-based approach. The problem is, photoreceptors are very different from ISFETs. In the case of a photoreceptor, when a photon is incident, energy is transferred, you have the electron-hole pair generating, and the photon disappears in essence. Well, in the case of our ISFETs, once an ion comes into the field, it sort of decides to hang around. And that's where the problem comes in. And this is what we term as gate voltage accumulation. So we looked at a lot of data from our past chips, and we found out something super interesting. The non-ideal effects are spatially correlated. In simple terms, ISFETs that are closer together will show similarities in the non-ideal effects. So they'll have similar trap charge, they'll have similar drift. And we said, let's depart from the pixel-wise approach or the global approach. Let's go to something which is more local global. That means clusters, and take inspiration from these neurons. Well, that brought us to the question, can we make our pixels smarter like neurons? And so there have been multiple models of different behaviors of neurons, like regular spiking, intrinsic bursting, chattering, fast spiking, thalamocortical responses, resonator, and low threshold spiking. And what we wanted to do was mimic the intrinsic bursting or the thalamocortical. And that's what we've achieved in this paper. So now look at this device. You have this ISFET, right? It has some analyte on it. It starts to spike at a certain frequency. Then happens the DNA amplification because of the lamp assay, because we've heated the surface here. And so it starts spiking at a new frequency, but it continues to spike at this because of gate voltage accumulation. Well, what we decided to do was that let's allow it to spike at a certain frequency, but as soon as amplification occurs, it goes, hey, me, I've seen the amplification, right? Me. That's what it's doing here. After that, when gate voltage accumulation starts to occur, it stops spiking at the same frequency. It slows down again. And so you see that we can detect a region of amplification inside the pixel. We had something that we did in the past where we were just trying to convert our input ISFET signals into spikes. So you have a voltage clamped input structure that tries to charge this membrane capacitance. Once it crosses the threshold of this integrate and fire first inverter, it will cause a huge current to be fed into this membrane capacitance, causing a spike, which then automatically discharges because of the second spike that's generated here, which is fed into this reset circuit. This is a slew controlled inverter. And so you can control the rate using this control point, which is the refractory period. What we did was brought in a new channel, which is the calcium conductance channel, right? And we tried to reduce the number of transistors earlier with a common gate configuration. What this allows us to do in essence is it causes a second branch of current, as you can see here. And now this Q9 starts fighting with this Q11 when it comes to charging the same membrane capacitance. And what happens? Well, it spikes, right? It spikes at a certain frequency, starts spiking faster when that amplification event occurs, but then that calcium conductance channel starts pulling it back down and it slows down again. So this is your membrane capacitance charging. You have this feedback spike that comes in and the refractory period, which you can control as a control point. So I became super happy. I started running all these amplification sensitivity experiments. And I was like, oh, okay, if there's a 6 millivolt change, there'll be a 10 kilohertz burst. If there's a 36 millivolt change, there's a 60.98 kilohertz burst. And so I'll be able to see all this happen. I go to my supervisors, right? And they're like, oh, yeah, I really like the concept, right? Pantelis is super happy. But then he's like, well, will it work with the time resolution of nucleic acid amplification, which is in minutes? Of course it doesn't, right? Too many bursts during the amplification. PhD student can never get it right the first time. And so I go back to literature and I start delving around and I find something interesting. People have sort of tried to stimulate cycling through the reference electrode and try to get rid of drift at a certain angle. I did not want to use a big capacitance. You can just increase the size of the capacitance and you can slow everything down. But this is something novel as well, where now this is the real data from one of the past chips where we vary for 2 minutes by 34 millivolts due to amplification. A further variation is due to drift at 150 millivolts for 45 minutes, right? That causes the slope. And then we finally, this is what we add, is a pulse of 10 millivolts of 10 seconds with a pulse width of 5 seconds. And this is varied through the reference electrode. And what do you see? That's the spike burst, right? So that happens there and we're able to figure this out again. When you look at everything that exists out there, I think we've made a huge jump this time because this is the first approach where you're doing something within the pixel itself. Also, as you can see, the power consumption is very low, ultra low, 25.71 nanowatt to 323.8 nanowatt as compared to everything in the past. That's because we've slowed everything down. You see, this was in tens of kilohertz and we've come all the way down to hertz. And so that's the reason we're saving all that power. So in conclusion, we have a novel approach for on-chip nucleic acid amplification detection by relying on in-pixel processing. We've used calcium conductance channel to induce the intrinsic bursting, which can help us detect a burst spike due to the onset of amplification. Finally, we can help the pixel ignore that gate voltage accumulation problem that it always sees, and it operates at an ultra low power. Our next step is to implement the complete inhibition of spiking. So what I want is I do not want it to spike at all when there's no amplification event. So it stays silent, spikes a lot, and then stops again. And so that's something that we're now trying to work towards. That's the thalamocortical response. And finally, we want to use on-chip neural networks to give amplification detection classification. So you do everything on chip, And at the end, you just get an answer whether there's a problem or not. This chip is currently being sent for fabrication in TSMC 65 nanometer. So yeah, we did change processes after we wrote the paper, but hopefully we'll have great results for you soon. So thank you to the group. They are instrumental because we are a multidisciplinary group with biologists and everyone involved. And yeah, I'm open to questions.